Hello everyone, hope you can all hear me. My name is Pedro and I currently work as a software engineer. Before that I used to frequent a lot of hackathons in the UK, and today I'm going to be talking a little bit about graph databases. Oh, it's good, looks like you guys can hear me. So I'm going to get started. Just want to let you all know that if you want to get in touch with me to ask any questions or anything relating to graph databases on Neo4j in the end, I'm Pedro M on Discord or PEDSM on anything else. So if you want to ask me on Twitter or anything else, just let me know and I'm going to be happy to answer any questions. All right, so getting started. So I'm going to be talking about graph databases and I'm going to be using Neo4j as an example, but a lot of the concepts that I'm going to be talking about here apply to any other graph databases. So if you decide that you like the idea of this, but you're not a massive fan of Neo4j that I'm going to be showing, do feel free to look into other alternatives for it. Just to start, if you want to try all these examples that I'm going to be showing to you, you can go to neo4j.com/download and get Neo4j for yourself and try it all out, or you can install it through Docker. Is quite straightforward. If you're familiar with Docker, you can do something along the lines of that and get it all up and running. But I'll let you guys take a look at that later. I'll also make sure to send links to these slides and Discord afterwards, so if you want to go through all of this at your own pace, feel free to do that as well. So talking about graphs, I think one of the first important distinctions that you have to make when talking about graph databases is that when you say graph, a lot of people's first image that comes to their head is something along those lines. And that is fine, but when we are talking about graph databases, we are actually referring to graph theory, something more like this. So if you've ever done some graph theory either in maths or a computer science degree, you know that a graph is slightly different to that previous image, which is more of a chart, and it's basically a series of vertices and edges. But in computer science, we kind of took those names and we kind of distorted them to be more like what we like to call them. Computer scientists love to rename things, so we call them nodes or relationships. So if you look at an example of this image here, when we represent our data in a graph format, we have nodes such as Alice here, and have relationships which relate a node such as Alice to another node such as Charlie, and then we can create this sort of network effect. So a lot of times graphs are actually called networks, and there's a big branch of study on network analysis, which is actually just the study and understanding of graph structures like this one. So I'm gonna be referring to these as nodes and relationships because that's what most graph databases refer to them as. But if you're doing your own research and you ever come across the terms of vertices and edges, you can know that vertices are nodes and edges are relationships. They're just different names for the same thing. One of the things that is really, really nice to work with something like a graph is that if you ever had to model a database in something like maybe MongoDB or MySQL or Postgres, and you had a whiteboard next to you, you often end up designing your model in a whiteboard in sort of a graph shape. And this is something that Neo4j in particular is quite a big fan of, is what they call the whiteboard model. When you're talking about data or what sort of interactions your application is going to have, it's very easy for you to draw some circles on a whiteboard and connect them with some arrows. And that model that you create on a whiteboard or a piece of paper or anything very easily translates to a graph database. So that is a huge advantage if you can put your ideas into a whiteboard and then convert it to your database without having to think about, I'm going to need some tables here, I'm going to need to have some relationship tables. All of that extra work that you would need to convert your whiteboard model into a database is something that a graph database kind of takes away from you having to do manually, and kind of just works intuitively as you would expect if you're familiar to drawing a bunch of squares and pointing arrows to them to demarcate those relationships. So I think whenever talking about databases, it's quite important to kind of compare this new paradigm to paradigms that people are familiar with. So if you're familiar with any SQL-based relationship-focused model for data structures, you will often end up with something like this. You have a table which will contain your employees, and those employees will be related to departments. However, you can't simply have a one-to-many relationship on a SQL database because you cannot have a unlimited amount of fields in which a single employee can be related to a department. So what you often end up having to do is creating an employees table, a departments table, and then you have to create a department members table, which will then relate the employee to the department. So let's say Alice here is employee number 815. We can then say that 815 is part of department 111, 815 is part of department 119, and 181. And this is fine. This works great and has been used across industry over and over again and has been proven that it's a model that works. However, it's not quite as intuitive as a graph model. And when it comes to query that data, it becomes a little bit more tricky. So if you take a look at an SQL query that you would use to fetch that information, you would start off by selecting a name from that person, and then you have to join that person to the person department, and then again you're going to have to join that person department table with a department table, and kind of end up with this triple left join here, just to get a information that should be quite trivial. Which department is this person in? So if you convert that to a graph model, we change quite a lot of things and we get rid of a lot of things, but we replace them with some others. So if you think about Alice here as a node, our departments are also nodes. We can simply have a relationship between Alice and our department straight directly from node to node without having to have that intermediate table to do the normalization. Here we can have as many as we want, and here we have 3 relationships. And just looking at this picture, if you don't have a lot of computer science knowledge and you don't understand relationship databases that well, I think this is quite a lot more intuitive from the start. So for you to be able to understand that Alice belongs to this department and this department and this department. It's also important to note that in the majority of graph databases and in the majority of scenarios, your relationships will be directional as well. They don't have to be 100% of the time, but if you see here, Alice has a belongs to type relationship to a department. And also here we are adding labels, which we are saying that Alice is a person and A42 is a department. So these somewhat replace the concept of a table, but I'm not going to compare them too much because they're slightly different. They are more like the concept of a tag in systems where you can tag things into multiple categories, because you don't necessarily have to have a single label for a node. A node can have multiple labels. So looking at what that query looks like in Cypher, Cypher being the query language that Neo4j specifically uses. So this is not every graph database, but it's the one that I'm going to be showing to you. This is what that same previous query in SQL would look like in Cypher. Cypher uses pattern matching rather than a select notation. So what we do here is we say, I want to match a node. So here using the parentheses here, we are specifying that this is a node of type person, and I'm going to call that node B for later reference. And then I have a relationship here, which we use this kind of arrow notation with a little square brackets here to denote a relationship. And that relationship is a works at, and here we have a direction to our department node, again using the parentheses here, D. And then we can, similar to SQL, say where d.name, which is the name of that department here, is IT department. And then we can return whatever we want from that query. So here I'm fetching p.name, but I could actually be fetching all sorts of things from there. So I'm going to do a little demo and kind of walk you through a couple of Cypher queries. One of the really nice things about Neo4j is that not only it provides Cypher, which is a really powerful language, but it also provides you with a browser graphic UI. So if you install Neo4j, you can of course programmatically access it and query it with the multiple libraries and drivers for Node.js, Java, and all sorts of different languages, Python, anything you can think of. They pretty much have a driver for you. And if not, they also provide a REST API, so you can build your own drivers if you really want to. Here, this sort of browser is what you get by default. If you spin up a Neo4j server, it actually has 3 ports, one of them being for this little web UI. So I'm going to be showing a lot of things in the web UI, just so that you can see the results of what we are doing. So here very quickly, I'm going to show you how to create a node. I think is one of the most basic things that you can do. As I mentioned, a node is represented by the parentheses here. So I'm just going to create a node of type person. I'm going to call this node just n for further reference, and then I'm going to say that this is a person. And Cypher here uses a notation quite similar to JSON, so if you're familiar with that, you will kind of understand what I'm doing here, which I'll simply do name, and here I can type a name and have it just run like this. So here, what I just did is I created a node of type person with one property, name, and the value of that property is Pedro. If you are familiar with SQL, this might seem a bit weird because we didn't define a structure for this type. In Neo4j, you don't actually have to define your structure for your nodes. Nodes can have optional properties and don't have to follow a schema per se. Although it is good practice to have a schema so that developers know that person will always have the same values available to them is not necessary. So we can just start creating nodes straight away. But as you can see here, after I ran that query, I got added one label, created one node, set one property, completed in this amount of time. So here I didn't have this person label, and I didn't have this node, and I didn't have this property. So Neo4j just straight up created everything for me. So you don't have to create your labels beforehand or anything like that. You can just create your nodes and all the data will be there. But one of the things that we didn't do here is we can't actually see what we created. So the web UI actually has this handy little feature where you can just say, please get me all of the things on that label. So if you see, when you query something in Neo4j, at least on the web browser, it's going to give you this sort of interactive view where you can actually see your nodes and kind of interact with them. Because Neo4j understands that visualizing your data in this manner is a lot easier for you to understand and kind of get insights on your data. Of course, you can see this data as a table, and it provides you all sorts of ways to seeing this data. But one of the other things that we could do is if I were to create another person, and I can call this John, I could also return the node that we're just creating from this bit to our query. So this is a very common pattern when you're working with Cypher, because you often create or update something. You can simply just, after creating it, return it straight away so that you have a view of that. So as you can see, not only did that create a new John node here, it also returned it. So now I get the nice view where I can actually see what I've just done. So if I, again, click on my person node labels here, you can see that now we have these 2 nodes. That is great, but this is not actually doing much for us because we could have done this in any sort of database and I achieved the same result because we're not actually having any relationships here. So next step, I guess, is to show how would you go about creating a relationship. So one way of doing that is you first need to get your nodes. So I'm going to call my first node A, so we can have node A and B and create a relationship between them. And I can specify that this node A is going to be a person. I don't have to, but it just makes sure that I'm selecting exactly the one thing that I need. And then here I'm just going to say where A.name equals Pedro and B.name equals John. So if I just, to test this before I start creating things, I just return A and B, and you can return multiple things like so, and should this run? Here we can see that we're just matching those 2, and then we are returning them. So now that I have my A and B matched to the things that I know I want to create a relationship from, I can make create, and I can say A. I don't have to specify that this is a person anymore because in this query, you already know that A is a person. And then I can create a relationship, and every time you create a relationship, it's going to be directional. So that is a dash and a greater than sign, and then B. And here, I'm going to have a relationship, which I'm just going to call R. And I'm going to say that this is I'm just going to call that friend. And one thing that Neo4j also allows us to do is that relationships can also have properties on their own. So I could say something along the lines of since 2020. So I can say that Pedro and John have been friends since 2020, and the since data is stored in the relationship itself, not in either A or B or the B nodes. So if I create that now, you can now see that you have a Pedro here. Pedro only has an ID and a name. John has an ID and a name. And if you click on the relationship, you can see that the relationship itself has its own properties. So that is quite handy if you want to have multiple relationships that can be created with different circumstances, and allows for a lot of flexibility for you to define characteristics of a relationship without having to modify the data of Pedro and John, for example. So I'm just going to get rid of these nodes and start with a slightly different example. So one easy way to get rid of all your nodes and relationships is that you can match all your nodes and all your relationships, but you need to make sure you do a optional match as your second match, because not all nodes may have relationships. And then to delete, as you may have expected, you can simply delete NR. So I'm matching all the nodes and also all the relationships, and then I'm going to delete all the nodes and relationships. That's going to clear everything. So if I now match all nodes and then just return that one, as soon as I don't specify anything to my node, then Neo4j is just going to pick up everything that matches, and then we can see that there is nothing here. So the next example that I'm going to walk you through is an example that I've actually written in a blog article for Neo4j. So if you want to take some more time to actually go through details of it, I am going to be posting a link for it later on Discord, so you can just go through it, and it goes through every single step that I'm going to go through here, and you can take it on your own time if you are trying to follow along later on. So this example that we're going to create is we're going to basically be mimicking a social network follow system. So if you think of something like Twitter, where you have multiple users which can follow multiple other users, and those users can have posts, we're going to try to recreate that at a very small scale, or at least demonstrate how that would be created inside of something like this. So one of the things that I'm going to start on is I'm going to create a constraint on a user. So I'm creating here a user label that doesn't exist yet, and I'm just going to ensure that user.email is unique. So this is how you would set up what would be the equivalent of a primary key in SQL. Here we're going to create a bunch of users on this database, but I want to make sure that the email of our user is always unique. That prevents us from having multiple users with the same email. And that means that if we ever want to refer to a user, we can just refer to their user through their email and be sure that there is no two users with that same email. So I can just create that. Just created that one constraint. And I'm going to create a user. So I'm going to create here John. John is a user, and John is going to have two properties here. John's going to have a name, John, and he's going to have an email of john@example.com. And I'm just going to return John here so that we can see what that actually looks like. Nothing different, I just added a new property to what we had before from our previous creation, and you can see that we created a user John here. Now I'm going to create our second user, Pedro, and I'm going to leave the email the same, just to demonstrate that we're going to get an error, because we've defined that users can only have unique emails. So that will prevent you from having two different users with the same email, which is something that you might want to do depending on what kind of application you are actually building. So I'm just going to change that here. And you can note here that I've left this and this as John. These variables that we use in our Cypher queries are only existent through the duration of this query. So I could call this John and return John, and it wouldn't make a huge difference. But for the sake of making our queries readable, I like to make sure that I use things that are generic, or I only use things that are specific when I know they will be specific, just so it makes it easier for people to read queries and you don't expect return John to return a node called Pedro and things of the sort. If I create that now that's created with no issues because there is a different email. Okay. So how would you go about creating a post? Very similar to what we would done before. We create a relationship and we create a post, and then we link all those bits together. But what we can do is a slightly different query, which combines all those steps that we've seen before to create everything in one single query. Why would you do that? Because in this example, if a user is creating a post, we don't want a post to be created without a user. So we don't want to create the post and then attach the relationship from the post to the user. We actually would rather create the relationship and the node together so that we never have a dangling post that has not been created by anyone. So what would that look like? So first we can get our user. So let's say that John has written a post on our social networks of sorts. Apart from using the where clause that we've seen before, where I could say where john.email equals that, we can also use this slightly different pattern matching syntax where I can just straight up write John's email.com, and that's just return John here. So we can fetch John doing that, or we could have fetched John by doing where john.emails equals john@example.com. Either way is valid. I like the first way a little bit more just because it's a little bit cleaner in my opinion. It makes it very, very obvious that we're talking about the email of John and you don't have to care too much about your variable names. But just to let you know that you can do both ways. If you're familiar with SQL, you might want to use your where statements just because that's more familiar to you. But either way is an option. So here, knowing that we already have John and John is matching to the correct thing that we want to create that post for, we can add to this statement a create, and we're going to say that John here has a relationship which is pointing to him. We can either make it pointing either way depending on what we think is appropriate, and the relationship here is going to be of type created by, and then here I'm going to create a post of type post. My post is not going to have a lot. It's just going to have some title, my first post, and some content. And here I want to return John. I'm going to return R for the relationship, and I'm going to return the post. If I wanted to, I could also add a property here to say created at and when this was created, but for this example we don't really need to do that. So if I don't have any mistakes on that query, oops, if I just missed the line here to indicate the relationship between the post to the relationship to John. So if we do that, now we can see Neo4j quite nicely colors our different labels, different colors. You can change those if you want, but they are just for display purposes. Here we have John, and when I click on John, you can see that email john@example.com, name John with a automatically generated ID of 0. The post has an ID of 3 and has its content and its title. And we can see that our relationship here exists and has a direction, but it doesn't actually have any data on it because we decided not to put any data on it. Okay, so that is how you would create a post. So if I just come around here and I click on this, this is just going to do a match all query. So if you see here, match all nodes and return all nodes, and this limit 25 here and then is just to make sure that if our database happen to have 1,000,000 nodes, we are not going to try to render 1,000,000 circles, or no browser will be able to handle. But this is the current state of our database right now. We have a Pedro node here, a John node here, and we can see that a post was created by John. So at the first glance, you can already see that it's very easy to understand the data that you have by just looking at this, and it allows you to do very interesting analysis very easily by just looking at certain users. So one more thing that I want to show you from the Neo4j browser is that if I were to actually just, let's say, fetch all my users and return all my nodes here, if I get the John node here, the browser also allows us to expand and edit everything that is related to it in a what we call one-hop relationship, where it's directly related to. So if you have a lot of data imported into Neo4j, you can do a lot of exploratory analysis by just poking around here without even having to do a lot of queries. So that is a very great tool, even if you're not building an application per se, but you just have a bunch of data that you want to analyze. You can just import all that data here and kind of just go through it with this graphical interface. But just to add a little bit more complexity to our database here, I am just going to open up another, just do one more example, which would be how would you create a follow relationship between two users. So if Pedro were to follow John, and then how would we be able to get things such as all the posts that a certain person has done. So quite similar to what we've done before. If I just pull up the query that we had before, we're still going to be matching John because we are going to be doing something to John here, which would be creating a relationship from him. And then we can just get rid of this bit. And what I'm going to do here is just say that we are going to have a second user that's also going to be matched. Here will be Pedro, it's also a user, and we can match him by his email, knowing that that is unique. So I can just grab his email and drop it in there. So now I can create a relationship of type follows John. Pedro now follows John. You could revert this to be Pedro on this side and John on this side if you change the arrow, but I'm just going to leave it like this for now. So if I just return those, and that should create our follows relationship now. As you can see, Pedro now follows John. And if you look at the whole database, it just looks something like this. Very basic, very straightforward, and very intuitive for you, someone that hasn't actually ever worked with a graph database, to just understand what this data actually means. So the real power of graph databases comes when you're actually trying to get some data out of the database rather than just creating it. So one very common query that you would have to do is, if you were logged in as Pedro as the user, then you would like to see all the posts from all the users which you follow. So in Neo4j, that is really straightforward to do, because all we have to do is to say, let's match your user first. And we can say that we are matching it by email and say Pedro at example.com. So I'll just return you for now. You can see that this is matching Pedro. So what I want is, I don't actually want to return the user, I want to return some posts. So here I am just going to say a query. I'm not even going to name this, I'm just going to say that there is a relationship of follows to your followed, which will be users, and then I want to get all the posts which were created by that person. So if you look at this, followed here, what we are getting is, we are getting the list of follow people that Pedro followed. In this case, it's just John because it's a very small example. But then if there were multiple people, you will be able to see multiple people. And if you want to get a post, we can just say created by, and then here we can get the post, which would be of type post. So instead of doing that, I can simply return posts. This would actually be posts in the case that there are multiple ones. And boom, you can get that data, which it's two relationships away, very quickly, without having to worry about how am I going to set up my database? How am I going to structure my queries? And how am I going to make those queries into queries that are efficient? Graph databases are very efficient on this sort of queries, so there is no such worry of having to use things like query planners to understand the execution plan of a SQL query to know if your query is going to execute in a good time. You can just kind of work with highly related data very, very easily. And one of the last things that I want to show you is how to then get this data in a way that it actually makes sense for your application. So right now we've just been using this graphical interface, which is quite nice if you're kind of trying things out and you want to explore and you want to click around and see where does this actually come from or what is actually related to this. But if you look at the output that this query actually produces, it might not be exactly what you want. So Neo4j actually has quite a handy feature for that, which is called mapping. So a lot of API these days uses JSON for transferring data. So Neo4j actually works quite nicely with that. So if you just, for example, do something along the lines of match user, and here I'm just going to match John one more time. John, actually for this example, I'll just match all the users because why not? So here, this will match all my users. And you can see you're getting a JSON representation of that straight away. If you were to have more data that you don't want the API to return, so let's say that John actually had this password here. Actually, let's just quickly do that. So let's just say I set u.password secret. So here we just added a key to both users with a secret password. You wouldn't want necessarily to get the password of the users every single time, because if Pedro is requesting data on John, there's no need for us to be passing that information around. The database can just keep that for when it's actually needed. So one thing that we can do is when we are matching all our users, we can return you, and then we can use this little syntax here to say what is that we actually want. So let's say we want the user's name and we want the user's email. And that's enough. We don't want that password. So we can specify exactly what is that we want to be returned. That data is still there, but we're just not returning it because we might not need it for that specific use case. With that, we can also do slightly more complex queries, such as if we were to try to fetch all the posts that were created by a certain person. So if you get a created by here, you could then add all the posts that that person has created. We could then add a special key and use this collect function here, which will simply do p.title, which is going to convert this list of posts, because there may be more than one post that one person has created, and just put it in a nice little JSON array. So if I do that, now we can see that we fetched John here. Is there a slightly, yeah, there we go. That's a slightly better view. We fetched our John user here and had its posts and its email. I think if we just slightly tweak this to be match you here, that will now fetch both of our users. Because what was happening on our previous query is that we were trying to match all the users and their posts, but that may be a case scenario where a user doesn't have any posts. So here we get this really nice restructured data, which says name, post, email. So basically you can conform that data into whatever format that you want for your application, so that it works quite nicely without you having to think about how you're going to model that data in whatever it is that you're doing. You can just put data in and extract data out as JSON, which you're going to find a library to work with in pretty much any programming language that you're using. So that goes for my demo. There's of course a lot more stuff that you can do with graphs, and I like to say that graphs are everywhere. That is a phrase that Neo4j is kind of using as their slogan everywhere now. But if you want just a couple more examples of what you can do with graph databases and graph data structures, a couple examples are semantic trees. So if you ever work with natural language processing and you're trying to understand how different words relate to each other, making syntactic and semantic graphs like this are very good to representing text data and the context of them. They're also used for things like Google's PageRank, which is their ranking algorithm and how they decide which search results to prioritize. That is basically a graph algorithm, which you can easily do with Neo4j. In fact, there are open source plugins which you can install inside of Neo4j to get that functionality with a simple, I think it's like a 4 or 5 line query, and you can just implement Google's way of ranking things. And more recently, one thing that caught my interest is the concept of knowledge graph. Knowledge graph, again, by getting Google, is how Google creates their responses for their Google Assistant. So they model all the information and knowledge that they have on any sort of content into a graph, and they use that in order to query and get responses. So if you have a Google Assistant and you ask for it to do anything, such set a timer, that is in the back end a knowledge graph that is understanding the language and converting into actions. In the end, if you're also into artificial intelligence and you've worked with any sort of neural network, you would clearly see that all neural networks are basically complex graphs that take inputs and convert outputs. So if you had to model your neural network in a way that you can understand or visualize, then a graph database would be an absolute great choice to do that, given that most of these neural networks are fairly large. So that is pretty much for it from me. Thank you. If you have any questions, do let me know. I will be on Discord and I will post links to a couple more code examples of Cypher and links to where you can get Neo4j and everything else. That's it for me.